Hello everyone. Welcome to this presentation on MicroStrategy Advanced and Predictive Analytics, a special edition with focus on the healthcare industry. My name is Rick Pector, and I'm very pleased to be here with you today. Allow me to lay out the agenda for this presentation. We'll start by talking about the top trends in analytics today, and then focus on how the MicroStrategy platform is an ideal analytical engine for delivering on those trends. We'll spend the majority of our time today focused on a couple demos that showcase MicroStrategy's unique approach to analytics. The first demo is a fun, somewhat tongue-in-cheek deep dive into Twitter analytics, and more seriously, how MicroStrategy covers the complete spectrum of analytics. Then we'll talk about some advanced analytics focused on the healthcare industry, and in the second demo, we'll deliver a real-world healthcare reimbursements forecasting solution and pull back the curtain on 7 state-of-the-art features that deliver predictions that are an order of magnitude more accurate than typical approaches in use today. Finally, we'll wrap up with a discussion of next steps and best practices, plus we'll share links with you to both demos so you can play with them on your own. So with that, let's get started by talking about the top trends in analytics today. Our partners at BARC recently published their survey of almost 2,800 business intelligence professionals and what they think the big business intelligence trends are for 2017. The reason why I'm including this survey is because it highlights many capabilities you'll find in MicroStrategy in the talk I'm giving today. If we focus on just the top 7 trends, they're all things that MicroStrategy does extremely well, from self-service data discovery to metadata and governance, and most importantly, what we're here to talk about today, predictive analytics. Since we're talking about trends, let's go back in time and compare the results of this survey to the year before. Interestingly enough, of those top 7 trends, the 3 that have ranked up are self-service, data governance, and predictive analytics. Now that last one is music to my ears. I've been working at MicroStrategy for nearly 2 decades now, and most of that time has been spent developing features for advanced and predictive analytics. As a solutions architect, I want to dive a little bit deeper into the MicroStrategy architecture during this talk because it's fundamental to understanding why MicroStrategy's capabilities are unique when it comes to advanced and predictive analytics. MicroStrategy was organically built from the ground up to support any analytical solution, deploying insights to people on the front lines in easy-to-use tools via the touchpoints they're accustomed to. Now, MicroStrategy is not a tool, it's a platform, and to better appreciate what that means to you and your business, let's focus on how the MicroStrategy platform turns data seamlessly into advanced functionality in ways none of our competitors can claim. Now, I'm a firm believer in maximum information density, and this diagram is a fairly detailed schematic of the MicroStrategy platform architecture, from getting at enterprise assets at the bottom to delivering that information out to users at the top. I'm going to simplify this a bit for our discussion. We won't be focusing today on our services and tools. And let's simplify this even more to focus on how we take data and deliver results to users. The focus today is on how we leverage our metadata to deliver those results and fill the gap between an organization's data and the people on the front lines. Now, the power of metadata is that it serves as an abstraction layer, hiding the complexity of accessing data stored in various databases and files, cubes and tables, rows and columns. Instead, users can focus on common business rules and definitions without needing to understand the details of how that data is sourced. Metadata literally means data about data, and you can think of MicroStrategy metadata as a governed database that precisely defines how data is accessed and turned into definitions that are consistent across the organization. But all that data is really just a bunch of ones and zeros. Analytics are the engines that turn data into knowledge and insights people can use, so let's focus on the analytics that MicroStrategy supports. This is the MicroStrategy Analytical Map, and it breaks down analytics into 3 main areas. We have an analytical function library, which has over 350 functions out of the box. We also have a set of native predictive algorithms that enable MicroStrategy to build the most commonly used types of predictive models without requiring any third-party tools. Of course, there are a lot of tools out there, and so we support PMML, the predictive model markup language, which allows MicroStrategy to score models developed by other applications. And for everything else, we have integrated R, an open-source language and environment for advanced analytics. R is the world's most popular analytical toolset with millions of users and over 8,000 packages and growing. R covers the broadest range of analytics that any organization may need. Let's dive down into our analytical function library. As I mentioned, we have over 350 functions available out of the box, no special packages to load or licensing required. Here's a sample of some of the more interesting functions and the domains they cover. When it comes to predictive analytics, things are a little more sophisticated. This chart is the most recent Rexer Analytics survey of over 1,200 data scientists worldwide. When looking at this chart, I encourage you to focus on the blue bars, which represent the techniques used most often. Not surprisingly, regression, decision trees, and cluster analysis are at the top. These three techniques are commonly called the three workhorses of data mining, since the vast majority of objectives can be achieved with just these three algorithms. Now, I would add a fourth workhorse for time series, since many MicroStrategy customers and users in general turn to time series algorithms for delivering forecasts. The check marks are techniques that MicroStrategy supports natively out of the box. No third-party tools required. Our objective when adding these techniques to the MicroStrategy platform was to cover the handful of algorithms most commonly used in analytical applications. And as you can see, we met that goal. We support regression out of the box. We have implemented the CART algorithm for decision trees. You can leverage our k-means algorithm to build cluster models. We can do time series thanks to our native exponential smoothing algorithm. And you can do things like market basket analysis courtesy of our built-in association rules algorithm. The target symbols indicate techniques we can do via PMML. For example, you'll notice that while we don't natively build neural network models, we can natively score neural network models generated as PMML from other tools. The same thing goes for other techniques like support vector machines and rule sets. But notice for everything else on this list, R has it covered. That was a key factor into why we chose to add R to the platform, and why I'm so excited about the solutions made possible by the combination of MicroStrategy and R. Now, because R is so popular, most vendors have added an R integration to their offerings, but MicroStrategy's support of R is unique and better. To understand why that is, we need to go back in time, back to how the MicroStrategy platform was architected in the first place. Let's go back in time to the year 2000 and the release of MicroStrategy version 7. Version 7 release was significant not only for the transition from 16 to 32-bit, but also for the platform architecture that we use today. At its core, the MicroStrategy platform is implemented in a language called C++. And thanks to the platform's well-defined application program interfaces, or APIs, by design, new functions can easily be added using C++. When I joined the company back then, I often heard MicroStrategy referred to in the media as a data mining company. But data mining is synonymous with predictive analytics, and, geek that I am, I knew that while MicroStrategy was the best at business intelligence and analyzing data stored in enterprise data warehouses, there was only limited support for taking that rearview mirror data and projecting it ahead into the future. So one of the first things my team and I did was to create the function plugin wizard. In fact, when you install the MicroStrategy platform, and if we detect the right version of Visual C++ on your machine, we'll add the function plugin wizard to your Visual C++ environment, and it will create a new code project for you, literally with places in the code that say, to do, add your code here. Function plugins allow our users to write their own custom functions and deploy them to MicroStrategy, adding new functions to the platform that we didn't include out of the box. Even to this day, using our developer client, you can still write your own C++ functions and import them into your MicroStrategy projects, and these functions will execute using the same high-performance engine and benefit from all the same platform features like security that our native functions do. But this does require some coding skills with C++, which of course my team had, and we actually used function plugins to add the algorithms you saw on the previous slide. When it came to R, we used the same approach to build our R integration pack and the set of R script functions that it contains. In addition to the fact that R, as a higher level language, is easier for users to write their own analytics in, MicroStrategy's R analytics are simpler to use because they are deployed as regular metrics using any MicroStrategy metric editor. But what's really cool about MicroStrategy's approach to R is our unique ability to support R natively in our platform. As you may know, as an open source technology, R is licensed using the GNU public license, which can be thought of as a copyleft license. You're free to use R as long as you make the source code freely available. Well, thanks to our unique architecture, which was built from the ground up with function plugins in mind, It was easy for MicroStrategy to do this since the R integration pack uses the same function plugin source code we've been making openly available for years. In fact, we openly licensed the R integration pack using the less restrictive than GPL Apache freeware license. Why is this important? Because unlike most other vendors who have to use an R server to isolate their code from R, MicroStrategy can execute R code natively just like all of our native analytics. When you think about it, there are some clear advantages if you can avoid requiring an R server just to integrate with R. Because of MicroStrategy's unique architecture, we have what one of our partners described as the best R integration in the industry. And here's why. Requiring an R server means you must acquire and administer that server, either a physical box or a new instance in your cloud, adding cost and administrative overhead that can be a barrier to entry for many applications. MicroStrategy doesn't need an R server. We can execute R natively. Some vendors charge extra to use an R server, either through special privileges or commercial licensing. MicroStrategy doesn't. If you can create a metric using MicroStrategy, you can create an R analytic in the same way at no additional cost. We have a very unique approach to deploying R analytics. While most vendors embed R code in line to deploy an R analytic, we reference a standalone R script. This means that one script can be made generally available to many applications. And if I need to make a change or enhance that script, I can make those changes once, and any and all applications that use that script will pick up the new code automatically. That script can be protected using an ACL, it can be version controlled, it can even be edited by RStudio and persisted using source code control tools like GitHub. Conversely, solutions that embed R code in line will force you to find any and all instances of that code if you want to make improvements. So our ability to reference a single version of the code R script is something unique to MicroStrategy that gives us advantages in usability and ensures that the latest, greatest version of the analytic is getting out to all users automatically. MicroStrategy metrics include the ability for users to control parameters of the analytic without having to touch the source code, allowing a single R script to generate unique results customized for each application. Most other tools, if you want user-controlled parameters, you may have to do special handling, you may have to create a new table in the data warehouse or jump through other hoops in order for users to customize an analytic to their needs. Also be on the lookout for a statement in the fine print that says performance is inversely proportional to security. If you have an outbound server that you're copying data to, then you're going to want to ensure that connection is secure. You may want to ensure additional security is there, and each layer added tends to increase latencies and hamper performance. With MicroStrategy, you don't have those concerns. We're not moving data outside of our environment to an external server just for calculations. In fact, as a native high-performance engine, you get all the built-in security features that come with MicroStrategy. Security is just built in and there is no trade-off to be made. Finally, when it comes to deploying these analytics, other tools can require special handling. Oftentimes, results come back in the form of a table or a view that has to be digested and modeled. With MicroStrategy, results from R analytics are deployed like all other metrics, and it's really difficult to tell if a calculation came from R or one of our native functions. In addition, we support vanilla R, with no restrictions on versions or packages you can use. With over 8,000 packages out there, it's great that MicroStrategy can support all of them, and not all vendors can claim that. We also handle and log all errors because in the real world there can be data anomalies, you may have a bug in your code, and the ability to report and log such occurrences using the normal means is important. I could go on, but I'll close this out by mentioning that MicroStrategy is able to persist the entire R environment from an execution as an R data file, for instance on an error or at the completion of an R script. I can open that R data file in a tool like RStudio and see all the objects and their state. Finally, all that said, MicroStrategy can optionally support an R server when one is required. There are times when an R server would make sense, for example when performance or data scalability demand one. But that's an option, and for the vast majority of applications, an R server is just not required. So what can we do with all these analytics? Well, I'll ask you to bear with me. Let's jump into our first demo, which is intended to be a fun one. Have you noticed that our president likes to use Twitter? Of course we have, and Donald Trump's use of Twitter has been unique, first as a presidential candidate, and even more so as president. Now Donald Trump won the election, He is our president, and we all need him to be successful. What follows is not only bipartisan, it's nonpartisan. This is not intended to be about politics. Rather, I want to have a fact-based discussion about Donald Trump's Twitter feed using a variety of analytics made possible by the combination of MicroStrategy and MicroStrategy NR. Now, Donald Trump is a prolific tweeter, and you may have noticed a certain irony in his tweets. For example, the day after winning the election, Donald Trump tweeted about protesters who were being very unfair. That was followed just 9 hours later with a tweet loving the passion of the protesters and saying, "We will all come together and be proud." Similarly, the day after the inauguration, President Trump tweeted again about protesters and how they hurt the cause badly, only to follow with another tweet less than 90 minutes later saying that peaceful protests are the hallmark of our democracy. In both cases, we have tweets written in two different voices. Could they have also come from different people? Well, to answer that, let's go back in time to 2016 during the presidential campaign. During that time, it was noted often in the media that Donald Trump uses more than one device to tweet, including an Android and an iPhone. Furthermore, that the Android tweets tended to be harsher than the iPhone ones, leading many to surmise that multiple people in fact have access to Donald Trump's Twitter accounts. This was actually confirmed by Trump in a tweet protesting the terrorist attack in San Bernardino, California, when you may recall that Apple refused to break into the suspect's iPhone. Earlier in 2016, Trump tweeted, "I'll only be using the Samsung until they, Apple, give the info." Now, Samsung devices run the Android operating system, and Apple never did give the info. Federal authorities were able to crack open the iPhone on their own. Fast forward to 2017, since about 50 days in office, the @RealDonaldTrump account stopped sourcing tweets from an Android device, and the @POTUS account Donald Trump began to use after becoming the 45th President of the United States has never sourced tweets from an Android. In fact, this was confirmed in a tweet from Trump's social media director, Dan Scavino Jr., that indeed, Trump has stopped using an Android and has begun using an iPhone. So we know Trump uses different devices, but are there truly different people tweeting for Trump? And if so, how can we predict which tweets are from Trump since he no longer uses an Android? Fortunately, we can use MicroStrategy and R to analyze the metadata from Trump's Twitter feed and test the hypothesis that, at least for Twitter, Donald Trump used an Android and not an iPhone. So with that background, let's jump into a dashboard built using MicroStrategy Desktop. Now this dashboard is also available on the web, and at the end of this presentation, we'll be providing links to it so you can play with the data yourself. This dashboard is connected into Donald Trump's Twitter feed, and when you connect to the Twitter API, you get a lot more information about each tweet than just what was said and when. Most importantly, we can see details about the device that sourced each tweet. As you can see in the upper section of the dashboard, we have a good sample size of thousands of tweets from Donald Trump. First of all, throughout this dashboard, the color scheme will be consistent. Orange represents Android, and blue represents iPhone. Plus there's a small number of tweets from up to a dozen different devices, which will color in green. If we focus first on the tweets sent during the campaign and as president-elect, some interesting patterns become visible. Given that time, about half of the 2,500 or so tweets were sourced from an iPhone in blue, slightly less from an Android in orange, and less than 10% were from other devices in green. The top tier of the dashboard is focused on behaviors we can discern from the Twitter data, and some interesting contrasts appear. For example, less than 10% of the tweets from an Android contained a picture or a link, while about 3/4 of the iPhone did. Now, if I'm running a political campaign, like any marketing program, in order to better engage with my followers, I'm going to include a picture or a link or other content, a call to action, focused on keeping their attention on my message. That's behavior consistent with the iPhone here, while the Android rarely demonstrates that strategy. Less than 10% of the Android tweets contain a hashtag, while about 50% of the iPhone tweets do. What's really interesting is that not all of Donald Trump's tweets are from Donald Trump himself. Roughly 1/4 of the Android tweets are actually retweets from other people. Conversely, less than 2% of the iPhone tweets during this time are retweets. One new feature that I've added recently is whether the tweet ends in some kind of punctuation, like a period or an exclamation point. Nearly 9 out of 10 tweets from the Android have this feature, while only 1 in 5 from the iPhone do. Next, let's focus on the popular response to Trump's tweets, and allow me to expand on this bubble chart, which has the number of times a tweet was favorited on the x-axis and the number of times a tweet was retweeted on the y-axis. We can see that orange dominates the most popular tweets found in the upper right. Keep in mind that followers reading tweets on Twitter are not normally told the device that sourced the tweet. And remembering that orange equals Android and our hypothesis that Android equals Trump, it would appear that the tweets from Donald Trump himself resonate most with his followers. The middle tier of this dashboard is focused on the timing of the tweets. Now, Donald Trump is famous for his early morning tweet storms, and when we look at the tweets by hour of day, that becomes evident. The tweets from the Android peak in the early morning hours, when tweets from all other devices are just getting started. We can look at the daily timeline of the tweets, and one thing that becomes clear is that there's a drop-off in the volume of tweets from the iPhone after the election. This would be consistent with campaign staff using the iPhone to tweet on Donald Trump's behalf, since, win or lose, most campaign workers are out of a job after the election. What's also notable here is the big increase in tweets from the Android device that occurred after the first of the year. Finally, we can look at tweets by day of week, and in particular focus on Sunday, when most employees would be taking a day off and correspondingly has the fewest tweets from the iPhone, but that is the second most prolific day for the Android. At the bottom we have a grid with all the details on each tweet. I'll also tip my hand a bit and point out the rightmost column labeled Predict Consensus. As you'll see in a minute or two, we'll be using these features to predict which tweets are from Donald Trump. And if I undo my time frame filter, you'll notice that starting at about his 50th day in office, there's no more orange. With the exception of 2 tweets on a weekend late in March, since day 50, Donald Trump no longer tweets from an Android. Fortunately, we can use this information to build predictive models. But before I do that, we need to dive into the content of the tweets themselves. Now, everything so far has just been looking at the metadata, which describes the tweets without any details on the tweet's content, its message, or more specifically the words used and the sentiment behind those words. The top tier of this dashboard looks at the words contained in the tweets. Of course, we've thrown away all the common words, the ofs and the thes, and we removed any words that appear fewer than 5 times in all the tweets. Now, Trump once famously said, "I know words, I know the best words." Well, these are his words, so let's see what they say. Remembering that orange is Android and blue is iPhone, let's look at the word clouds first. A quick study shows that, while both devices include words echoing campaign rallies, words like Hillary and crooked, some are more frequent on the Android. Conversely, the iPhone has prominent hashtags, while none are present in the Android word cloud. Next, let's turn up the contrast and study the top-ranked words for each device, specifically, words skewed to be more frequently on one device versus the other. We even calculate the log odds, which are positive for words more likely to be found on an Android and negative for words more likely to appear on an iPhone. Not surprisingly, 7 of the top 10 iPhone words are hashtags. Interestingly, 2 of the top 10 Android words aren't technically words at all. Next, thanks to R's tiny text package, we can analyze the sentiments found in each tweet. While sentiment analysis is definitely an advanced analytic, like most things in software, it's very straightforward once you know the secret. This is simple word counting, combined with a 14,000-word English lexicon that maps each word to 8 different emotions, plus general categories for positive and negative, and a numeric measure of each tweet's positive-negative polarity. As you can see on the bar chart, the iPhone tends to be more positive and contains a larger proportion of words associated with joy and trust. The Android is more negative and contains proportionately more words associated with sadness, disgust, and anger. The radar plot is basically the ratio of each pair of bars on the bar chart. Anything greater than or outside the 1 circle is more Android. Anything less than 1 or inside the circle is more iPhone. It's notable when we change the selector to the post-election transition period when Donald Trump was president-elect. While somewhat amplified by the small sample size of just a few hundred tweets, the tweets leading up to the inauguration from the Android appear spiked with anger, sadness, and fear. Once again, at the bottom of this dashboard, you'll find all the tweets and their details, plus, of course, our predictor. And that's what we're going to focus on next. Let's take all these stats, let's use them to build some predictive models, and we'll make some predictions. First, allow me to describe the predictive modeling process. We use tweets from the campaign and transition periods, everything prior to the inauguration, a period where we had good activity on both the Android and the iPhone devices, but before Trump started to use the @POTUS account, and before any national security actions might have been taken to better secure the president's devices. We partitioned these 2,500 tweets into two sets. We used a random sample of 80% or roughly 2,000 of those tweets to build predictive models, and we held out 20% or about 500 tweets for model validation. We built 6 different predictive models. We have an ADA boost model, a generalized linear model, which is just a fancier name for a regression model, a neural network, a random forest, a support vector machine, and a decision tree too. You may have noticed that the models don't always come up with the same prediction. As I'll explain, there's a reason for that, having to do with how each algorithm finds predictive power from the variables describing Trump's tweets. That diversity is a good thing, and we use a simple voting scheme to build a consensus prediction. If 4 or more of the models predict a tweet is from Trump, then that's the consensus prediction as well. Otherwise, the tweet is predicted to be not Trump. You can see all the input variables here, and while we include the device source on the grid, we don't use that stat in any of the predictive models. That would have been a giveaway. It can be fun seeing if you agree with the consensus prediction, especially in cases where there's a split decision from the 6 predictive models. Now, making predictions is simple data science. Models are built to be easily scored, but there's a bit of an art to understanding why models behave the way they do, something that's important to understand when deploying any predictive algorithm. Plus, there's good descriptive insights to be gained by explaining how each model works. This allows us to answer questions like, why don't the predictions always agree, and which models are better? Of the 6 predictive models, 3 lend themselves to visualization. The easiest model to understand is the decision tree. All decision trees have a root node at the top with all the records, and the algorithm looks for the best variables to split the records so that one result begins to dominate. The first variable our decision tree used is word odds. Tweets with negative word odds are found on the left branch, positive word odd tweets are on the right. Next, we split on whether the tweet had a picture or a link. At this point, we reach our first leaf or terminal nodes, which are colored in gold. If word odds are negative and there's a picture or a link, then the prediction is not Trump, and about a third of our tweets meet this criteria, and over 99% of those were not from an Android. On the right-hand side, if the word odds were positive and there wasn't a picture or a link, then the prediction is Trump, and about half of the tweets match this criteria, and 82% of those were from an Android. Hour of day and end with punctuation were used to classify the final 20% of the tweets. So out of 17 variables, we can easily see how this decision tree just needed 4 to make predictions. Long story short, decision trees are powerful to visualize, intuitive to understand, and that's one reason why they're so popular. The next most understandable model is the generalized linear model, which can be represented using a standard regression equation. If the result of the equation is positive, then the tweet is predicted to be from Trump. Otherwise, negative results are not Trump. All the variables in blue are numeric. The binary ones are 1 when true, 0 when false. The coefficients in black represent the weight the algorithm gave each of the variables. Eyeballing the equation, you can see retweets and ending with punctuation are weighted most heavily for Trump. Having hashtags, pictures, or links were weighted most heavily for not Trump. I'd agree if you think this is not as intuitive as the decision tree, but it's not too hard to noodle your way through the math when you think about it. Let's contrast these 2 visualizations with the neural network on the right and its characteristic butterfly pattern of weighted connections between neurons. While beautiful and elegant, it's exceedingly difficult for us mere humans to look at a neural net and understand what's going on. For all intents and purposes, neural networks are black boxes. The remaining 3 models don't lend themselves to graphic visualization. The best we can do are these esoteric text descriptions intended for the data science types out there. But that's not the end of the story. thanks to the tools we have in our toolkit that work equally well on all of our models. This dashboard has 7 columns of information, one for each of our 6 predicted models, plus our consensus on the right. The top tier is where you'll find the confusion matrices, which measure how well each model performed against our holdout validation data set of roughly 500 tweets. These are the tweets that were not used for training the model, and we'll compare the predictions from each model to the actual known correct results. You can see the green diagonals for the true positives and true negatives, and in red are the false positive and false negatives. This information is conveniently summarized in the middle tier, and it's worth noting that the most accurate model overall was the random forest, and that the overall accuracy of it and our consensus prediction is about 90%. In other words, we should expect our consensus prediction to be wrong about 1 time in 10, and that's something important to keep in mind. Finally, we can see the importance each model gave to the 17 variables. Note that all the algorithms rank the variable importance differently, and the neural network favors a different set of variables from all the rest. Next, we built lift charts, which allow us to compare how well the algorithms do in finding the tweets most likely to be from Trump first. If we compare the area bounded by the theoretical most optimal model and a naive random model, with the area bounded by the predictive model and the random model, we get a different model performance measure called ranking quality. The random forest and the AdaBoost models have the highest ranking quality. How else might we use these predictive models? Well, I recently heard a segment on National Public Radio about an application that trades stocks in companies that Trump mentions in his tweets. Imagine building such an application. Wouldn't it be good to know when a tweet is likely to actually be from Donald Trump? And wouldn't it be even better to do some sentiment analysis to know whether he said something positive or negative in the tweet? Fortunately, 3 of the algorithms are supported by the PMML standard, and it was easy to export from R the PMML for the decision tree, the generalized linear model, and the neural network model. Because MicroStrategy supports PMML, it's easy to envision building such an app. You would import these 3 models into predictive metrics, and use a 2 out of 3 voting scheme to buy stocks Trump is positive on and short stocks he tweets negatively about. Finally, there's one more tool we can use to understand how each of our 17 variables relate to each other, thanks to the off-the-shelf R script we have for pairwise variable correlation. On the main diagonal are histograms that show the distribution for each variable. The upper triangle shows scatter plots for each pair of variables with a best fit spline. The lower triangle of the grid shows the correlation between any pair of variables on a scale of +1 in blue for variables directly correlated to -1 in red for variables inversely proportional to each other. One thing I'd note is the strong correlation between ends with punctuation and has picture or link, indicating that they're somewhat redundant and perhaps we don't need to use both in our models. If you'll allow me to belabor this demo one topic further, there's another way of looking at Trump's tweets that we haven't considered, mainly because we've treated each tweet as independent from the rest. Recently, a paper came out that studied the relationship of timing between tweets, and how this information can be used to determine if the tweets were generated by a bot or not. In other words, for a given tweet, we can measure how long it's been since the last tweet and how long it will be until the next tweet. The authors of this paper simulated different timing distributions and compared those to tweets from actual humans, tweets scheduled by humans in advance, and tweets from bots generated algorithmically. Because the patterns for Trump's Android tweets are different than those from the iPhone. Humans have daily patterns, and they tend to have quiet periods, in particular for sleep. Because of this, when humans tweet, you'll see a pattern for the last tweets of the day, when there's a long gap until the next tweet, or the first tweets of the day, when there's a long gap since the last tweets. Trump's Android tweets have a bit of a hole in the center, indicative of this human behavior. Bots, on the other hand, aren't restricted to the circadian rhythms of humans, and oddly enough, Trump's iPhone tweets don't have such a hole. Bottom line, this points to evidence that not Trump tweets may also be not human tweets, and instead, some may be the work of bots. So with that, let's jump back to the presentation. I have to acknowledge David Robinson and his varianceexplained.org blog, which sparked the idea for building this Trump demo in the first place. It's a very lucid, yet statistically rigorous discussion that includes cool explanations of how he used R to do the math. And if you're interested in more details, please Google search Variance Explained and Trump tweets to learn more. Now, I'd be the first to acknowledge that it's a bit dicey to include such a politically charged subject as Trump tweets in order to demonstrate the powerful analytics possible with MicroStrategy. And I thank you for taking this demo in the nonpartisan spirit intended. It does have the benefit of being a relevant topic regardless of the industry you work in, and isn't it refreshing to have a fact-based discussion, especially when it comes to Donald Trump? More importantly, we did see a wide range of analytics at work, and we covered the full range of analytics any organization might need, simply by focusing on one thing: tweets. We built descriptive statistics that counted tweets in a variety of ways, by device, by time, by account, by feature. We dove into those tweets and looked at the words contained and diagnosed the sentiment behind them. We built predictive models using those descriptive and diagnostic variables, and we use those models not only to make predictions, but also to understand better which factors are consistent with tweets from Donald Trump and which may not. Finally, we leveraged simulation and time maps to further optimize classifying tweets, not only as from Trump or not, but also bot or not. And so, the Trump Tweets dashboard showcases all the types of analytics an organization might need and deploys them in an intuitive, easy-to-use dashboard. As I mentioned, we do have this dashboard on the web, and at the end, we will give you a link to it. Now that you've seen what MicroStrategy Analytics can do, let's drop down a level of detail into how they actually do their work, and the added capabilities made possible with a combination of MicroStrategy and R. All MicroStrategy functions return one of two types of data: scalars, or single values, and vectors, an array of values. Let's call these in-band analytics because they return results directly to the grid during a MicroStrategy execution, just like we're used to with all other tools, for instance, like Microsoft Excel. But with our R engine, we're able to return results that go beyond the grid. Let's call these out-of-band analytics. For example, R analytics access an R script that's secured from the file system and only referenced by our metadata, not stored there. We have the ability to interact with the resources on the web. For example, while I could have used the MicroStrategy Data Import Connector for Twitter, the Trump Tweets dashboard uses R's TwitR package and its user timeline function to get the tweets output from Trump's accounts, and not just anybody who might have referenced Donald Trump's handle in other tweets. I can also save images. I can persist R objects and environments as R data files. I can save tables as CSVs or Excel files, or push those tables into cubes. And I can do all this using the same framework as traditional analytics. All MicroStrategy functions fit into one of three classes. There's what we call a generic function that takes in vectors and outputs a vector, processing a table at a time. For instance, when I build a predictive model, I need to bring in the entire data set as a collection of vectors, process that data set, and return the results as a vector of predictions back to the grid. I'll contrast that with the simple functions, which I can use when I apply a predictive model, which does calculations a row at a time, taking in the values for each variable as scalars and spitting out the score as a scalar. The third and final class of functions are aggregation functions, which take in a vector and output a scalar. Sum and average are a good example of aggregation functions. Now, when order is important, we have sorted versions of the generic and aggregation functions, like when forecasting a time series or doing aggregations like moving sum and moving average, the order is important. So while there's really 5 types of functions, they all fall into these 3 general classes, and all analytics, including our R analytics, are able to do these in-band capabilities. But in addition to that, with R analytics, we optionally have the ability to do some interesting new things. For example, if an R script depends on a package and that package has yet to be loaded on the machine. If the machine has access to the internet, our R script can automatically download and install that missing package with no human intervention required. We can interact with the file system. We can store images there. We can output PMML, as I showed you. Starting in version 10.9, we've released our RESTful Push API, which allows an R script to push that data into a cube so it can be used with other analytics. Finally, I can use R to change the compute context and push analytics out to an outbound R server, or use R packages like SparklyR to orchestrate the execution of advanced analytics in big data environments like Hadoop. So R opens up a whole new range of capabilities and workflows that MicroStrategy can tackle, innovative analytical solutions that just wouldn't be possible otherwise. And MicroStrategy does this in a way that makes our analytics indistinguishable from regular analytics. And with that, let's shift gears and focus on healthcare and the solutions MicroStrategy can deliver for this important sector. MicroStrategy has a wealth of top healthcare companies that we work with, and here are just some of the logos we can claim. From payers and providers to hospitals and research institutes, MicroStrategy has delivered a wide range of applications for our customers in the healthcare industry. For example, the current opioid crisis has killed more than 60,000 people nationwide in 2016. That's more than all the U.S. servicemen and women killed in the entire Vietnam War. We can help that crisis by providing information that helps target areas that need the most focus and helping prescribers be smarter in an effort to reduce the number of prescriptions and therefore the flow of opioids into these communities. Next, let's focus on two key measures in healthcare today. Hospital readmissions is a quality measure and a key factor when it comes to reducing the cost of healthcare in this country. Technology is important, but integrating it into clinical workflows while also fostering an enterprise-wide appreciation of data-driven decision-making is essential to making data tools work for better population health. MicroStrategy has developed applications that help reduce readmits, which can save hospitals millions of dollars each year. Another key topic in healthcare today is average length of stay. And we've also developed solutions that identify opportunities for reducing average length of stay, in particular for a network of hospitals in the Midwest. Now, since this is a talk on analytics, let's look at a couple of ways to use analytics to manage and hopefully reduce average length of stay. Here's a chart that plots the average length of stay for a hospital over 3 years. Note that there appears to be a cyclical pattern where average length of stay increases to over 6 days and then decreases to under 5 in a repeating pattern. Now, when we overlay this data with the November to April flu season, there appears to be a correlation. But how do we know if the correlation is statistically significant? Fortunately, MicroStrategy's analytical function library includes a range of statistical tests we can use to test the null hypothesis that there's nothing special about flu season when it comes to average length of stay. We'll use the heteroscedastic t-test to determine the probability that average length of stay during flu season is unrelated to average length of stay when it's not flu season. This is actually a type of aggregation function where we take in two vectors and output a single scalar that represents the probability that average length of stay and flu season are unrelated. When we do the calculation, that probability is vanishingly small, about 10 million to 1 that average length of stay and flu season are unrelated. So we can reject the null hypothesis and conclude, yes, average length of stay is higher during flu season, and so extra precautions should be justified, perhaps by enforcing the frequent use of hand sanitizer and having ill or vulnerable patients wear masks to reduce the spreading of germs. We have also built applications that put average length of stay under statistical process control. Fortunately, R has no less than 4 different SPC packages, and the actual R script implementation is deceptively simple. This SPC-R analytic is a generic function that takes in a vector representing the average length of stay data and applies SPC techniques to set control limits and, in conjunction with rules, return a vector in band that detects when process controls are violated or when control limits are exceeded. But as an R analytic, we can use out-of-band analytics to deliver the control charts that are easily generated as part of the SPC package from R, avoiding the challenges of having to build a picture-perfect document that accomplishes all three of the SPC charts that we see here: the individuals chart, the moving range chart, and the process capability chart with its key statistics like CP and CPK. I think you'll agree that the out-of-band features made possible by MicroStrategy's R analytical engine are very complementary to MicroStrategy's in-band features and creates opportunities for new and exciting applications for the healthcare industry. In fact, as our final demo, let's see how far we can push the state-of-the-art using MicroStrategy and R. This is a real-world application developed in conjunction with one of our earliest and longest tenured customers, Hawaii Medical Service Association. Each year, HMSA processes millions of healthcare claims, resulting in billions of dollars in reimbursements. In fact, similar to how the Trump tweets dashboard focused on a single thing, tweets, this solution focuses on a single thing as well, but in this case, it's reimbursements. Allow me to level set you on the dimensions at play here. We're using 7 years of reimbursement data that has been obfuscated to have the same patterns, but not the actual data itself, so we're protected there. This demo has reimbursements from 3 different healthcare plans. We have a preferred care plan, which is similar to a PPO. We have a managed care plan, which is similar to an HMO, and an affordable care plan, which is like Medicare. Within each of these plans are a dozen different categories of service. Things like hospital inpatient, skilled nursing facility, radiology, pharmacy, labs, emergency room, and many others. So we have 3 plans, 12 categories, and about $1 billion per year in claims reimbursed, and that means a mere 1% improvement in forecast accuracy will drop $10 million from the top line. So the accuracy of these forecasts can have a significant impact on the amount of reserves required to meet regulatory requirements in order to pay future claims, as well as an impact on the premiums charged to its members. Before getting into the demo, I need to set up 7 state-of-the-art features that allow this solution to deliver forecasts that can be orders of magnitude more accurate. Many of these techniques are applicable to other domains besides healthcare, but there certainly are certain healthcare industry concepts that make this application so compelling. First is a topic that I frequently include in my talks, a topic called bottom-up forecasting using non-overlapping segments. Now, I have a saying that top line is for show, but bottom-up is for dough. And I feel that's important because you cannot manage a business from the top line. While there are times when it does make sense to report on the top-line performance of a business, especially for shareholders and for regulatory disclosures, if you want to truly manage performance, and especially if there's a problem or an issue, you have to be able to drill down into the data, because the devil is in the details. And so, what we recommend you do is something very common for business intelligence applications: slice and dice that data into non-overlapping segments. Now, as I mentioned before, there are 3 plans here, and we could break this data down by plan. Recall that there are 12 categories of service, and so we could segment the data by category. But what we're actually going to do in this demo is to use both plan and category to divide our business into 36 non-overlapping segments. Each plan category will be its own segment, and we'll build forecast models for each segment that capture the impact of factors that are unique to that particular area of the business. We'll use these segments as intuitive selectors that allow us to focus on the biggest drivers of performance. More on that in a second. Next, we have an example of an industry-specific analytic that, while esoteric, is easily solvable thanks to the wide range of packages available from R. In this case, it's an insurance industry concept called Incurred But Not Reported, or IBNR. To be honest, before I started working with HMSA, I had never heard of this term, but fortunately my customer had, and they had already in mind the R package to do the trick. I have a little video here that shows why IBNR is so important to the insurance industry. When an insurance company issues a policy, it charges premiums in exchange for a promise to reimburse future claims, and those claims are not known up front. This animation visualizes what we can think of as a 12-month policy that's issued each month. As time goes on, each successive month or development period of reimbursements can be made and used to estimate future claims that are yet to come. The result is a triangular structure, and we're able to use the trend of claims over time to predict future claims to come. Essentially, IBNR completes the triangle, so we're always accounting for future claims that predict what the final ultimate runout in reimbursements will be. In this demo, anytime you see a pink region peek out from behind the actual reimbursements made, that's the IBNR kicking in. And the cool thing about this is that implementing this feature was easy thanks to R's chain ladder package. Next is a feature common to all forecasting applications, the need to handle outliers. Outliers can skew an analysis inappropriately, and so we have automated the handling of outliers in this forecasting application. In this example, we have an outlier here that actually falls within the range of data. It's greater than the minimum value and less than the maximum value in the data set. In fact, if it had occurred in the final year instead of the first year, it probably wouldn't be considered an outlier at all. But clearly this data point is much higher than those surrounding it. So we use R's studentized residual to measure how far away each data point is from the actual trend. If it helps, think of the studentized residual as similar to standard deviations from a mean. A simple function parameter allows the user to specify the outlier threshold, the number of studentized residuals from that trend beyond which any value will be considered an outlier, and that value will be limited to that outlier threshold. Say we limit ourselves to plus or minus 3 standard deviations off the trend. Our outlier threshold, therefore, would be 3. And we would bring an outlier value back down to that outlier threshold limit. Now, we don't actually change the data in the data warehouse. We just handle the outlier before we feed the data to the forecasting algorithm, thereby reducing the impact of the outlier on our future forecasts. The key here is that this is done automatically behind the scenes with no human intervention required. You don't have to eyeball 36 different segments. Plus, users have full transparency into the data points that were identified as outliers and how they were handled. Of course, the name of this game is Predictive Analytics, and we're going to use a set of time series algorithms courtesy of R's forecast package. You may recall me mentioning earlier that MicroStrategy out of the box supports a time series algorithm called exponential smoothing, and that's something you could do natively with MicroStrategy. Fortunately, R has that algorithm as well. In addition to that, the forecast package contains ARIMA, autoaggressive integrated with moving average, which tends to be the gold standard when it comes to time series forecasting. If you've ever heard on the news about seasonally adjusted government statistics, usually there's an ARIMA algorithm behind the scenes doing the adjusting. But MicroStrategy doesn't support ARIMA, and neither does the PMML standard, as a matter of fact. Fortunately, the forecast package does. In fact, we'll use its auto-ARIMA function that searches through a variety of models looking for the best one. What's exciting is a new algorithm that, in working with HMSA, we added to the solution after our initial efforts had begun. This new algorithm is called STL decomposition. STL decomposition is turning out to be quite good at delivering high-quality models, and so it's a welcome addition to our application. Finally, there's two other algorithms that I won't call predictive. They're naive models, and a naive model simply assumes that the next value will be the same as the last value. There's also a seasonal naive model that assumes the next season's value will be same as the last season's value. These naive models are useful in setting the lower bound of model performance, for if a predictive model cannot outperform a naive one, then it probably isn't worth deploying. And we could use this in our automated process to detect when we may not have good predictive models at play. So with all these algorithms, we're ready to put them to work. We just need some data. Similar to how we held out tweets for validation in the Trump tweets demo, we're also going to hold out the most recent data points for validation of the time series models we generate. The question is, what's the right number of records to hold out? Well, rather than trying to pick just one, we'll simply try a bunch and see which one is the best. For each hold-in, hold-out combination, we use the hold-in data to build a test model and then generate test forecasts from the test models and compare that to the known hold-out validation data. The difference between the test forecast and the known hold-out data is called the residuals. And if you take one statistical term away from this discussion, you should know that the residual is what's left over when you subtract the actual value from the test forecast prediction. Residuals are the name of the game when it comes to doing time series forecasting. These residuals can be rolled up into model quality measures that basically average the sum of the residuals, or average the sum of the absolute value of the residuals, or do something along those lines. There are actually 6 different forecast accuracy measures, and users can pick their favorite easily using a simple function parameter. Now, for each hold-in, hold-out combination, we have a complete set of model quality statistics. In this demo, we have 7 holdout values ranging from 6 to 12, and we can summarize the results in a table like this. The best model will have the lowest values. That's going to be important for the next feature we talk about, champion-challenger model selection. So, putting things all together, we have 3 different predictive algorithms, plus the naive and seasonal naive algorithms, which we won't count as predictive. We actually build 2 models for each algorithm. A test model, which is used in model validation, plus we train a full model using all the data that retains the features of the test model. When we include the IBNR model, that's 7 different predictive models that we build for each hold-in, hold-out combination. And with 7 different hold-in, hold-out combinations, that's a total of 49 models we end up building for each segment. And based on those, we'll be able to determine which one has the best forecast accuracy, and it will become our champion and the model we'll use for making forecasts in production. Champion-challenger model selection is a key feature that has to be automated so that the best model is always selected automatically without any human intervention required. Now normally, our story might end there, but there's something interesting about how healthcare reimbursements are processed, and that's going to take me into our final state-of-the-art forecasting feature, backtesting and trim. When you think about the life cycle of an insurance claim, they do take time to process. Imagine if I walk out of the building today and break my leg by slipping on something. There will be some time before I'm able to report that claim. Then my insurance company will check my eligibility, they're going to determine the benefits I'm entitled to, they'll analyze the details of the claim, they'll review the diagnoses from my doctor, they'll run rules and make edits, and eventually they're going to settle the claim and pay out the reimbursements. But all of this stuff takes time. You can see the effect of this when you look at the trend line for our reimbursement data. In the long term, the trend for reimbursements is up, but that trend breaks downward in the near term. And that's just the nature of the delays in the claims processing workflow. While each segment is different, we need to understand the unique nature of the downturn and what we can do about it. Now, depending on the segment, claims processing can take days, weeks, or months. For example, when I go to my pharmacy to fill a prescription from my doctor, they're able to take my insurance info, go online, and validate my benefits, and do that whole process almost instantly, right from the pharmacist's point-of-sale terminal. So for drugs, the near-term underrun can be minimal. But things like hospital bills can take longer to process, and if the hospital has contracted services with external providers, say my anesthesiologist, that can take even longer to process the reimbursement. So sometimes, instead of being affected by the near-term underruns which can mislead us to thinking the trend is turning down when it really isn't, it can be better to ignore or trim the most recent 1, 2, or even 3 months of data when building forecasts. And so that's what we do. In addition to the usual process where all the available data is used to build forecasts, we repeat the champion-challenger process for each trim. Now users can control how many periods are trimmed via a function parameter they can change using the standard MicroStrategy metric editor without touching the code. In this demo, we'll build models with a trim of 1, meaning that we'll ignore the most recent month's data. We'll build models with a trim of 2, meaning that we'll ignore the last 2 most recent data points. And we'll build models that ignore the last 3 data points. We'll end up with champions for all these, but they're not the ultimate champion for this segment. How do we determine which trim is the best? Well, to do that, we'll do something called backtesting. Now, the ultimate test of any prediction is, how well does it compare to reality? That's why we do the holdout validation. Well, backtesting is similar, except that instead of validating models against the most recent data, we execute our process against data that we know has been completed or fully run out. Backtesting says, let's go back in time when we know things have stabilized, that everything has been run out. We simulate a bunch of forecasts and determine the accuracy of those forecasts. This will allow us to see which models give us the best trim. We're actually going to repeat the process 12 times over a full year of run-out data, and the results of these 12 backtests will allow us to quantitatively determine which trim is the best trim. Here's how. Recall that we've already built the non-backtest models for trims 0, 1, 2, and 3. So we'll use the results from our 12 backtests to determine which trim has the best accuracy, and that model will become the champion for the segment. So at this point, for this one segment, we've built over 2,500 predictive models. Now, thanks to our automated machine learning approach, we can easily accomplish this with MicroStrategy NR. Imagine trying to build all these models by hand. And that was just for one segment. Of course, we have 3 different healthcare plans in 12 different categories, so we have to do this across all 36 segments. In the end, that's over 80,000 predictive models built in order to generate the most accurate forecasts possible for all 36 segments of our business. And the dashboard I'll demonstrate in a second puts the power of all these sophisticated analytics into the hands of any user, from executives and business analysts to actuarials and data scientists. The good news is that customers like HMSA are reporting significant improvements in forecast accuracy, taking percent errors in some cases from double digits down to single digits, and in some instances reporting error rates under 1%. One last thing worth mentioning is the workflow that built all these models and delivers such accurate forecasts. This all started with actual reimbursement data from a database with millions of claims and billions of dollars in reimbursements. In typical BI fashion, we slice and dice that data into segments, and once each month, after the books are closed, we go into a mode where we train our predictive models. When in training mode, we go through each segment, and we go through each backtest and trim, and we're going to train models. When we train models, we take the data set, perform IBNR, handle any outliers, and use Champion Challenger to find the model with the best forecast accuracy. All our models are persisted into a model repository, and we use those models to generate scores and deploy those forecasts in reports, scorecards, and dashboards. Now, I only really need to train models once a month. For the rest of the time, I can change my train mode function parameter to false, and instead of building models, we use the already built models for fast scoring. Now, scoring models is always faster than building models, which enables very fast performance for users while hiding the complexity of building all those models. And next month, after the books close, I can simply retrain my models with the latest data, and any and all reports, dashboards, and documents will use those updated models automatically, picking up the latest, greatest forecasts and delivering the most up-to-date results to users and the touch points that they prefer. And so with that, let's jump into our dashboard demo. Again, I'm using MicroStrategy Desktop, but you'll be able to access the exact same dashboard on the web. Let's start with the top-level forecast, and allow me to point out some features that will be consistent with all the forecast charts you'll see. We have 7 years of data, plus a 1-year forecast horizon that represents the future. The known reimbursements will always be the blue area chart. The pink area you see peeking out from behind the known results represents the forecast from our IBNR model. The orange area is the trim forecast, and then we have our forecast going forward into the future. The red line represents the predicted forecast value, and we have 80% and 95% confidence bands. Those values are actually controlled by function parameters that you can change without having to touch the code. In this chart, we've also included a simple linear trend line, and we can see that trend tends to fall within our confidence bands. I'll restore this chart to expose the rest of the dashboard, and you'll see I have a bar chart representing all 36 of our segments. We'll use this bar chart as a selector, and in typical data science fashion, let's focus first on the biggest drivers of performance. The top 3 segments are all categories of the preferred care plan. In particular, hospital inpatient, drug, and medical services. We can drill into those forecasts and see what's going on with these segments. Now, I could give this dashboard to my boss, and you don't have to be a data scientist to see what's going on. Now, in theory, our discussion of these forecasts could stop here, since we've made them all available for anyone to see. But for the data scientists in the room, there's a lot more detail we have available here, and so allow me to pull back the curtain on how these forecasts were made and all those models we built. First, we'll look at the champion for each segment. This is very similar to the forecast visualization we just looked at because it did visualize the champion. For this data science view, you'll notice that we've included the champion model's test forecast as well as the residuals in purple that resulted in this model being the champion. Remember that the residuals are the prediction error, simply the difference between the test forecast and the holdout actuals, and less is better. On the left-hand side, instead of a bar chart selector, we'll use a heat map to visualize and select our 36 segments, since the heat map conveys the same information in a denser format. Each segment in the heat map is sized by their share of reimbursements and colored by the champion model's forecast accuracy, where green is good, red is poor, and orange falls somewhere in between. For example, if we compare this segment in orange to this segment in green, we'll see that the confidence bands are much closer together. We can also see each segment's model quality and the statistic it represents. In this application, we're using mean absolute percent error, or MAPE, but users can easily change this using function parameters without having to touch any of the code. Now, this is just the winning champion model. And again, while this is really not intended for your boss or the CEO, data science types can visualize the challengers as well. In the upper tier of this dashboard, it has the same heat map and champion forecast we just saw. But down below, you'll find a bubble chart in the lower left with all 21 challenger models for this segment, and to the right, their forecast. Now there's 21 challengers because we use 3 different predictive algorithms, represented by the color of the bubbles, and 7 different holdouts, which position the bubbles on the x-axis. The y-axis positions the bubbles by the relative quality of the models they represent. We can see the winning model at the top, it's our champion. But we also see the 20 other challengers, and we get all the details, including the algorithm used, details about the nature of the model, and all the model quality statistics. What's really cool is that I could use the bubble chart as a selector and lasso, say, the top quality models and see their performance in the chart on the right, including their forecast lines and their residuals below. This is kind of similar to the spaghetti lines used in weather forecasts to represent different possible paths a hurricane might take. Here we can show how each forecast performs, and we also include an aggregation forecast, which is the average of the models selected. In fact, While we didn't choose to do this here, we could envision generating a new forecast that takes the average of the predictions from the top-ranked challenger models instead of just the top challenger model. We could see if that result is more robust and generates better forecasts than picking a single champion, and that's all possible because all the models are persisted in our model repository. We can even visualize the results from all those back tests that we did. Again, this is really just intended for data science types. We still have our segment selector and champion forecast on the top, but we can also see the backtest time frame. And down below we have details on all 12 backtests and the 4 different trims we used. The lower right has all 48 backtest and trims forecasts for this segment. On the lower left, we visualize all the residuals. Hopefully by now you'll know that residuals represent the forecast error, and less error is better. Therefore, less color is better. And this visualization represents the thousands of models that we built for each segment, and it makes it clear which trim is the best. For preferred care hospital inpatient, we see that a trim of 2 has over $1 million less than the forecast error if we had done the usual thing and didn't trim at all. On the other hand, as we expected for the drug category, which reimburses so quickly, we can easily see that the best trim is no trim at all. Finally, we can see using the best trim of 3 for medical services results in a forecast that is nearly 2% more accurate with a $2.2 million improvement in forecast accuracy. And so, all of this was done using a single MicroStrategy dashboard that I could share with my boss, I could share with my CEO, I could share with other analysts, and I will also share with you. Just one last visualization to share. Here's a summary of the predictive modeling results, including our top-line forecast. We summarize the algorithms and holdouts that are represented by the nearly 2,000 champion models we created. You can see all the modeling parameters that users can control without needing to touch any code. Finally, in green, during training mode we built nearly 20,000 models per hour, which took just over 4 hours to do. MicroStrategy can schedule this report so that it runs overnight once a month after the books close, and when you come into the office in the morning, the latest greatest forecast will be ready to go. Some closing thoughts and next steps. As MicroStrategy users, you already have all the tools you need. Everything I've shown you today is available from MicroStrategy at no additional cost. Because you have access to virtually every conceivable analytic and algorithm you might ever need, data mining is no longer a technology or licensing problem. It's really a people problem, and your ability to build and deploy advanced and predictive analytics is directly related to the knowledge, skills, and capabilities of you and the people in your organization. That's why it's a best practice to foster good collaboration between the demands of the business and the expertise of your data science team. But what if you don't have a data science team? Citizen data scientist is the new term for analytical amateurs, and while the learning curve can be steep, thanks to the resources from the R community, you're just a Google search and a YouTube video away from taking the next steps down that path. Better yet, leverage the knowledge of the MicroStrategy services team and our awesome consultants and our amazing consulting partners to fill any gaps and start the organizational transformation that impactful analytics make possible. Keep in mind this is an iterative process, so it's a best practice to iterate fast and iterate frequently. As you've seen, before deploying any model, be sure to validate it against records that were not used in training. Finally, be patient. If this was easy, everyone would be doing it. I want to thank you so much for your time. I know it was a long, jam-packed session. I hope you found it valuable. If you'd like to try these dashboards for yourselves, we've created tiny URLs where you can find them. Both dashboards will be available at tinyurl.com/MicroStrategy-Trump tweets for the Trump tweets dashboard, and tinyurl.com/MicroStrategy-Forecasting for the healthcare reimbursements dashboards. We also have videos associated with both those tiny URLs for video-Trump tweets and video-forecasting. When you access the dashboards, MicroStrategy Web will ask you to log in. Please use the login TT and the password TT, and you'll be all set to go. Thank you again for your time, and have a great day.